Imagine a smooth curve, not flat, like a planet's orbit, or a ball's arc. We study tiny changes along its path. A differential shows this. A tiny step, so small it's nearly straight, for an instant. This tiny step, that is it. It is the differential. A small change. In some quantity, some varying number. This change is super small, infinitesimal. Zoom on a curve. Keep going. That tiny piece looks straight. Almost. The differential captures this local straightness. It is the ultimate zoom. A concept. For variable x, dx is the change. For we, from x, dy is its partner. These are tiny conceptual shifts, ideas. Differentials, great for quick guesses. Called approximations. They are useful. Know your spot on a curve? And the differential's value there? You can predict the next tiny spot, like knowing speed and direction now. Differentials simplify hard problems. They help. They make big changes easy. Geometrically, what does it mean? See a curve under a powerful lens. At this micro level, it's a line, a tiny straight segment. It appears. Its x-length is dx, small, horizontal. Its y change is dy, small, vertical. These pieces build understanding. Locally, they show the curve's immediate shape. Recall slope, from school math, yes, rise over run. How steep? That is slope, easy for lines. Lines are constant, their slope is fixed. But curves, they twist, they turn. Their steepness varies, point to point. Differentials find slope. At one spot, a single precise cosmic address. We have dx, we have dy, tiny changes, infinitesimal. What now? Divide dy by dx. The ratio, this dy dx is something awesome, cosmic. It is instantaneous rate of change. The slope, right there, right then. Not an average, not a guess, the true slope. At that very point, picture that tiny straight piece, the one from our super zoom, its slope, that's dy dx, exactly. This is also the tangent slope. The tangent line, it just kisses. The curve at one point, same direction. Differentials find this cosmic compass. Why is this slope critical, so key? It shows how things change. Now, growing, shrinking, how quickly? Answers. For a planet, slope is velocity. For the universe, it's expansion rate, this power, describing instant change. Makes calculus with differentials mighty. Understanding cosmic motion, its rhythm. Tangent lines, what are they? They are lines of touch, special, in geometry, in physics, everywhere. A tangent meets a curve once at one spot, sharing its direction. Think of a sling, stone flies off. It follows the tangent. At release, differentials help us find them. How do differentials help find it? We found dy dx, that's the slope. Let's name it m. For slope. Know a point, x d y o on curve, and m at that point? Yes. The tangent line equation is simple. Y rho equals sine mx, xe. Basic. Differentials give m. The magic number. Geometrically, what's the deal? The tangent, best straight guess. For the curve. Near that spot. Zoom in. Very, very close. Curve and tangent almost merge. So dx and dy align, well, with the tangent. Local path. Why care about these tangent lines? Not just math theory. Far from it. They solve big real problems. Finding maximums or minimums. Optimization. Physics, direction of motion. Instantly. Computer graphics, smooth, sleek curves. Understanding tangents means power, insight, predicting futures, designing worlds. Cool. Real-world uses? Oh, plenty. Think motion, cars, planets, particles, position changes, over time, always. Plot this, position versus time. Curve. Differential of position, ds over time, dt. ds dt, that is velocity. Now, differential of velocity, dv over time, dt. dv dt, that is acceleration. Change changing, growth, it happens. See it, a star born, forest grows, universe expands. Wow, always. Growth rate links to size. Differentials model this dance. P is population, dp dt rate, how fast it grows. Now, more applications, yes, truly endless. Engineering forces, stress, strain in bridges and rockets, strong stuff. Economics, marginal cost, marginal revenue. One more item, what's the change? Medicine, drug levels in the body, how they change over time. Vital, tiny changes, big effects always. So differentials, tiny unseen shifts, but together, power, they unlock. Geometry of curves, dynamics of change, find slopes, draw tangent lines, see, understand motion and growth deeply from quantum bits to cosmic scales, differentials, a lens, a key. Small things explain the grand universe.